as the presentation title indicated, I will be talking about the medium voltage silicon carbide device, the gate drive for the device, and especially to use these devices for high voltage applications. So I will talk about the challenges and the two possible solutions, which are power over fiber and power harvesting from DC bus. And I would also talk about some of our current study on gate drive for 4.5 kV device, and at the end is a project timeline. So the project itself has multiple student members. We have one undergrad student member right now in the team who has high voltage trained. This project does involve a lot of hands-on high voltage experiments. So our PhD students are OSHA training certified. And in the next semester, we do have a high voltage class. It's called high voltage technology and experiments. So during that semester, we have 12 experiments, and some of them actually are a little bit hands-on, very routine high voltage AC and DC testings. And during the semester, we have already allocated one lab session for demonstrations of high voltage power electronics. So the outcome of this project will be in that demonstration together with a couple other topics. So we will make it a 2-hour demonstration of high voltage power electronics. So gate drive, partial discharge for airplanes, the partial discharge on the motor windings for airplanes, and also DC arc. So again, this project we hope actually not only have a very good technical outcome, but also good impact on education activities. So these are the slides you may have seen before in my first presentation on this topic back in July. So we do have a lot of high voltage devices coming in play. And recently we are also working with United Silicon Carbide on evaluating the superclassical device, the 4.5 kV module, which is a fantastic device actually. We are doing the double pass test of this device and we see very good performance. So with all these devices, we are looking at a lot of applications such as medium voltage drive, circuit breakers, SATCOMs, active power filters, fax devices, HVDC, and also solid-state transformers. And when we look at SATCOM, fax, all of this, and including the also HVDC, would involve very high voltage. So we are looking at medium voltage for medium voltage applications and also high voltage applications. And just a quick introduction on the gate drive itself. Basically, it has 4 functions, and we have the isolated power supply, isolated data transfer. We also need to have regular functions such as protection and gate drive. For the isolation for medium voltage devices, for high voltage applications, we need to have a very high isolation capability, usually over 15 kV, and we want to have a 0 partial discharge. And the biggest challenge by now actually is the high dV/dt. So this picture from spreadsheet back in 2014 actually shows we can have extremely high dV/dt up to 110 kV per microsecond. So it's something indeed make the design of the gate drive more challenging. And this is one example of power supply on top of the circuit. What you see is you have a huge toroidal core, and this actually gave you 20 kV isolation. But for this toroidal core, still you have coupling capacitance, and this capacitance is the perfect path for common mode current to go through. And no matter how you try, you cannot limit this or eliminate this capacitance. Basically, the best number we see so far is around 3.5 picofarad. And after this isolation transformer will provide regulated voltage to different loads on the gate drive board. And input to this transformer is low voltage. The reason we need to have such huge size is purely for insulation purpose. So it's a low voltage input, low voltage output, but high isolation. And to basically explain the common mode path, we have a picture here to show the coupling capacitance, and how the common mode current can go through different capacitance and the main DC source together with the 12-volt DC if you are using a power supply from M ground. And then if we look at this, we see if we follow this kind of structure with the circuit I showed in the last slide, we have a very high point on the 12-volt power supply. And if you look at the common mode voltage towards the transformer, what you see, indeed, actually, you have a high. Somebody was marching in the background. Okay, so what we see is, again, very high common mode voltage goes to the transformer, and with very slight coupling capacitance, you have high current, high common mode current. And then for the main functions, we do need to have a very high driving capability for fast switching, and we also need to make sure we have proper gate drive design, circuit designs to avoid crosstalk and have a very reliable protection. And this slide shows you typical electrical characteristics and the preferred protection functions of the gate drives. We see the supply voltage usually is at a low voltage end, but we need a very high voltage for isolation. We need to handle very high dVdt, and to make the control more accurate and also reduce the die time, we want to have a low propagation delay, or at least compensated propagation delay to make the die time smaller. And a pathwise distortion, we want this number to be less than 10 nanoseconds. Our switching cycle actually is not that long with high switching speed. So again, a lot of detailed, more detailed parameters we have to follow to design the gate drive. And for the protection, we need to have under voltage lockout, over voltage lockout, and we need to have a PWM signal overlap protection, internal protection, crosstalk prevention for Miller plateau, Miller capacitance, and if that's a thermocouple on the module itself, we can also realize a local shutdown based on the thermal information. And again, today I want to focus on the medium voltage device for high voltage, but I want to start with the example of devices that for medium voltage applications. For example, in this case, we are looking at 1.7 kV silicon carbide for 8 kV modular multi-level inverter, and we still have very stringent isolation requirement for this kind of application. The gate drive designed for this, later on I can explain, still needs to have a high insulation requirement, and the grounding scheme for this gate drive actually is very applicable to the medium voltage device too. So we start with the typical gate drive device. So this is a gate drive chip shown on this slide. We have on this gate drive chip we have two regions. One is a digital region, which takes in the digital input and send out the forward output and communicate with the microcontrollers. And on the other side, we have the analog, which drives the device. And in between, we have isolation, which is about 1.5 kV and with 1 picofarad. And this kind of gate drives now is actually very popular for high power devices, and for medium voltage, we can take advantage of what is already there, basically utilizing this in the driving stage. If it's a big device, we put a BJT or a MOSFET-based current boosting circuit at the end to drive a bigger device. So with that, actually, if we look at the traditional power stage, we have everything comes from the housekeeping power supply. It not only provides power to the gate drive, but also the DSP, FPGA, everything in the control. But we do need to have isolation between the control stage and the power stage. So that's the reason we have a 10 kV isolation DC-DC converter at a low voltage input, low voltage output, low power, 6 watt. And with this, actually, we would have isolated power for one circuit module. And in this circuit module, we have 2 devices, one up device and one lower device. The digital input to this device sharing the same ground, which is light green. And then we add 2 isolated power supplies to basically provide isolated ground for the real driving stage for the gate. So that's the green, that's the blue, and the light yellow. And if we look at the common mode, they have if we look at the common mode circuit, we can assume the switching stage is the AC common mode voltage source, and then the common mode noise will go through the insulation of the chip itself, as we showed in the last slide, 1.5 kV, 1 picofarad, and then the 3.3 kV isolation with 37 picofarad, and then goes to the main isolation stage with 10 kV isolation with 20 picofarad. But what you see is that this common mode current will go through the gate drive chip, and the ground here, marked by the right star, actually is fluctuating all the time. So it's really bad for the integrity of the control signal at the gate. So this is actually what we had proposed, and again, this is applicable to the high voltage device, medium voltage devices too. So we do not use a single 10 kV isolation. We use 2 10 kV isolation, and so we have 2 of these DC-DC converters. We separate the gate drive stage of the upper device and lower device 100%. And then on each device, we have another isolation power supply to provide the power needed by the digital stage, input stage of the gate drive board. So with this, when we look at the equivalent circuit for common mode current, what we see is that the common mode current from the source will go through the short circuit, because we do have a short connection showing in the main circuit diagram. And with this short connection, we finally can make sure we do not have any common mode current in the gate drive itself. So when we look at the differential input, so it's very power ground, and we have to test all kinds of devices to work out perfectly. So this is basically one of the actually with all kinds of regular devices and medium voltage devices. And then let's look at the tough challenges we have with high voltage applications. If we look at modular multi-level converter, we need to provide gate drives for the devices in each module. And the overall DC voltage for HVDC can be about 1 megawatt, and there are several 1 megawatt projects in China right now. So it is coming, but they are not utilizing silicon carbide devices. And when we look at this, we have the one option to provide the power to each gate drive with a centralized power supply, and this power supply shares the same ground with the main circuit. So the power source sharing the same ground with the main circuit. And then if we look at the case when all the upper modules are connected in series, which is marked in red in the circuit, but you would see that all the gate drives needs to sustain half of VDC. This means you need to have 500 kV isolation on the gate drive board. Thinking about 500 kV isolation transformer, that is huge. Actually, it's extremely difficult to manage just on a piece of PCB board for gate drive, which is very low voltage. So definitely for HVDC and effects, these are not applicable anymore. So then there are two possible solutions. One is power over fiber. The other is sub-module DC bus-based power harvesting. So we are taking power directly from the DC capacitor of each module. And you would say the second method maybe is widely developed for existing applications. Yes, it is. But when we are using higher voltage rated devices, the challenge is much higher, and we need to look at totally different approaches. But first, let me go through all the introduction, basically the power over fiber as one of the solutions. This is what we demonstrated in the last year. So we have a laser receiver, which is a multi-junction PV cell, and it has typical PV cell characteristics, and the efficiency is about 20%. And we use a regular laser generator, and we connect this to the receiver, and then we use this receiver to power on the gate drive. And with that, we eliminate all the common mode coupling between the power stage and the control circuit, and also all the coupling between upper and lower devices. So essentially, if you want to have 100% decoupling between everything, this is the solution. So basically, this is the most clean solution you can get. There are several technology challenges, but it's actually not that difficult because you still need to do the dummy load or power control for the receiver, and you still need to have a good circuit layout and so on, but it's a relatively much easier task when compared to the high voltage layout of the whole circuit. And this is basically how it looks like. So you have the laser receiver, and you have a very small gate drive board that is comparable with a small device. And we use this to drive a 15 kV, I believe it was a 12 amp device at the time. And we tried this with the bigger capacitance to verify the driving capability, and actually it works very well. So when you look at the gate drive voltage shown on this slide, actually it's pretty clean. And we also have very comprehensive protection. I think you have seen this slide before. Basically, we have the Miller clamping, and we have logical control, and also we have DSAT, which is marked in the yellow. And we did the test, everything. This is a test setup in our lab, and we have good, very clean waveforms in terms of regular driving, and I want to show you the results of the protection. So what we see here is a test setup. Actually, it's a test setup we used in the last year, and this year we rebuilt the power supply. It has much higher power capability, and now this is a double pulse test platform. And what we are looking at is the first test at 6 amp 500 watt. The purple curve is the current. It goes up, and after a certain point, you have a protection. So that shows actually it works out well with the low voltage. And then the next test, actually, we're at 5.5 kV, 9.5 amps. And again, the current goes up slowly. And eventually, you will see the protection when the current reaches 9.5 amps. And also it has a sharp shut down at that time. So it's almost there. So basically, that's what can be done with power over fiber. But today, I want to talk more about power harvesting from sub-module DC bus. So this is what we are doing currently in this project. So again, going to take the power from the submodule DC bus, and then each submodule DC bus only have a small portion of the overall DC voltage. But for a 15 kV device, this DC voltage can be more than 10 kV. And if we are using 20 kV device, this actually would possibly be 15 kV or even higher. So we are talking about to implement the isolated DC-DC converter with a 10 kV input and 15 watt output at a power less than 10 watt. And that's something extremely challenging. In the traditional solutions, people do have circuits to take power from submodules, and that has been done for many years, but not at this voltage level. For current MMC implementation with silicon devices, the DC bus usually is lower than 3 kV. So we are doing things 3 times higher voltage, and it's not that straightforward. So there are potential solutions. So we can have input series, output parallel DC-DC converters. So this actually is more or less like a solid-state transformer, but at a much lower power and much wider difference between input and output voltage. And this actually requires a lot of devices, and the gate drive circuits for these power stages will be also a challenge, though it would be very complex, and its reliability could be very low for a 10 kV implementation, because we do not want to use silicon carbide devices to drive the silicon carbide power supply for the main medium voltage device. So it's at this time, basically the device selections we have for this kind of circuits are silicon MOSFETs or silicon IGBTs with voltage ratings up to 4.5 kV. And then you do have another circuit option, which is multi-level DC-DC converters, and this is more like a switch capacitor circuit. Actually, in this you have the back capacitor. So this kind of, and you need to have a lot of devices in series, and it's very difficult to sustain or to realize the high voltage that we require. Another solution we recently see from a paper in, I believe this is actually from KTH actually. This paper shows tapped inductor buck converter, and again, this still suffers with a lot of devices connecting in series. So if we look at the pure power electronic solutions, we would say, okay, we are looking at a lot of very complicated circuitry, and with a very high voltage input, low voltage output, and a very small power. So these are not bad solutions. So so basically, in conclusion, we have all kinds of challenges that are faced by traditional solutions for taking power from the submodule DC bus. Then what should we do? How to reduce the cost and circuit complexity and realize high reliability? My thinking is always, let's start with things simple, and whether we can do things that are actually extremely simple and do the same job. So we start with voltage dividers. And if we look at voltage dividers, we have 4 kind of resistive type voltage dividers. And essentially, they're the same. You only have capacitors arranged to have better balance or have better stable voltage. And you can also build capacitive voltage dividers, and these capacitive voltage dividers is slightly trickier, and sometimes it's even not implemented. It's very difficult to implement because you will have very hard time to maintain the voltage on the capacitor. If it's AC circuit, it's easier, but this is DC. So capacitive voltage divider is not as good as a resistive voltage divider. So if we look at resistive voltage divider, what we can do is we can assume we have a very well-designed gate drive circuit, and it functions as a power load. And in this case, I just take a slightly educated number, 20 watt, which is definitely more than what we need for a power module, for most power modules. And then and that's very large background noise. Okay, thank you. So in this case, again, we are looking at one equivalent circuit that RL is your equivalent power supply for the gate drive, and R1 is the current limiting resistor, and these two form a voltage divider. And then if we do the calculation with simple equations, we can find out if we want the voltage on the voltage input to our gate drive to be 3.6, which is manageable now with silicon devices. We can basically have a very low power loss on the upper resistor, and also the resistance can be a fixed value. So overall, as together, the total power consumption on this circuit is slightly over 55 watts, and compared to hundreds of megawatts of power that is processed by the main circuit, this actually the efficiency loss is 0.01 or something like that. And then the problem is that when we look at our gate drive never has the constant power consumption. When the power consumption is not constant, it's a voltage divider, then the input voltage to our circuit will change. So at a very light load, our input voltage can be as low as several hundred watts, and then at a very heavy load can be close to 4,000 watts. And also the power loss on the upper resistor, which is purely to form the voltage divider, the pure loss on the upper device can be more than 80 watts if we have very low power on the gate drive. So that means we want to have our gate drive circuits to achieve constant power consumption to make sure we have constant voltage input to the circuit, and at the same time have a best efficiency of the circuit. So what we do is we will put a load compensation unit. We have one extremely simple circuit we designed to realize this function to regulate the power consumption of the lower arm based on the voltage we measured from the lower arm. And then we will have constant voltage, and from this constant voltage, which is smaller than 4 kV, we use traditional silicon devices and also auxiliary power supplies, which is very common in this kind of gate drives, to provide gate drive power and control power to drive this auxiliary housekeeping power supply for the gate drive to provide the gate drive power to the upper and lower device. I cannot speak too much on this. One thing is we are in the progress of developing this, and the other thing is that the patent application is in progress. We initiated this at OSU side, and we hope to start to work with PowerAmerica to go through the required procedures to file the patent before June next year. The reason is that this topic is already accepted topic for ECC Asia. We are organizing a special session on wide bandgap devices in ECC Asia in June in Taiwan next year, and this is a paper actually from my group that we would present. So from now, actually, we are looking at already one patent and also one possible paper out of this topic very soon. Hopefully, if everything's in place, it's definitely before this project ends. So then this actually are two solutions for the medium voltage devices for high voltage applications. So I think actually with power over fiber and the power harvesting from 10 kV and above DC bus, we finally can enable our medium voltage devices rated up to 20 kV to be utilized in applications where you would see voltage higher than 800 kV. So it's an enabled technology. And right now, what we are doing in the project on another parallel track, not only to design the new power supply stage, but also validate all the concepts on the grounding with our gate drive design and the testing of 4.5 kV silicon carbide unit. Again, this is from United Silicon Carbide. It's a super cascode device, and we actually are we already finished the static evaluation with curve tracer, and we are doing the dynamic evaluation of the device. And the gate drive board designed through this project, which started actually a little bit late because of the contracting issues, it's already in place. And we are using the traditional power supply structure. The power supply structure, as shown in the last couple of slides, is still under development. It's in the second phase of the project. So this is actually the test of the gate drive board with a low voltage device, because we have only, at the same time, I think only 2 samples of 4.5 kV module. I do not want to run the short circuit test with a limited number of modules first. So we use the 1.0 kV silicon carbide device to verify the short circuit function. What you see is that when the current, which is the green curve, is going up, eventually it is protected, and it's a MOSFET. So we didn't realize, this time we didn't realize the soft shutdown. So at the protection point, still we have the hard shutdown this time. So this is the test setup. So again, we have a newly built setup with the upper device, which is made of 1.7 kV silicon carbide Schottky diodes connecting series, and then this 4.5 kV power module as a lower device. We reused some of our components from our 15 kV gate drive test earlier, but the power supply is also redesigned. So this is a circuit diagram. Again, for this kind of experiment, it's extremely dangerous. Whenever we have experiments that needs to be run in the high voltage lab, not only our students are OSHA trained, also they are trained in my high voltage class. I have to be there personally to conducting the experiment with my students. So it's a fun project. For some other projects, I do not need to be there, but for this one, I'm always there to do the experiment. Then we are looking at some initial test waveforms, and we are looking at 10-on waveform with a little bit of slew rate. This is more defined by the gate resistance we are using right now. And for the 10-off, we have close to 50 kV per microsecond. So it's comparable with the numbers we have seen in the 15 kV device test earlier. And in the next few months, actually, in the next month was actually we will also try to increase the switching speed, either with this device or use other devices to create a higher dV/dt to test the immunity of the gate drive circuit. So the work summary is that we already finished the static evaluation of the super cascode device, and we finished our first version of the gate drive board design. We actually are running the double pulse test with our 20 kV rated system. So we want to basically build the second generation to improve the performance after everything's done. And then for the full summary of today's presentation, so the first thing I want to emphasize is that if we want to use medium voltage devices for high voltage applications, we still have a long way to go. It's still very challenging. And when we use the power harvesting from 10 kV or above DC bus, the existing solutions are not sufficient or too complicated for us to utilize. So we have proposed our own solutions, and also at the same time, we are basically working on the testing of a 4.5 kV device to also validate our gate drive designs, the regular functions, and also the protection functions. So this is the timeline of the project. So we are looking at the first 3 tasks. It's more about the 4.5 kV device to validate all our gate drive and protection functions. And meanwhile, we already started the design of the power supply for 10 kV gate drive to take power, harvesting power from sub-module. And hopefully, we will be able to do the demonstration by May next year and present this in the ECC Asia, which is in Taiwan. We do need one more paper in the special session. So if you want to contribute a paper to this, contact me. So this pretty much is all I have. And to end all my presentations, always have for power electronics. So if you want to save a life, engineer. Now questions.
Oh, thank you very much, Dr. Wang. That was a very good presentation, very informative. We have a couple of questions that have been submitted through the chat window, so I'll start with those.
Okay.
The first question is, what is the price of the power over fiber transmitter and receiver?
Actually, the price is very high at this time. That is one of the reasons that we're pursuing this power harvesting approach right now. Last time I talked with one of the suppliers of the receiver. They estimated the overall cost still would be several times higher than the transformer-based approach. But the material cost is very low. This is more about the engineering cost and the market. That's a very small market for that technology right now. The gate drive for medium voltage device is a target market, and the monitoring of high voltage equipment in substations, transmission lines is another application. So the material is multi-junction PV, but it's regular silicon-based PV cells, and they stack them together. So the efficiency is not that high, but the cost is material cost is low, and the biggest chunk of the material cost is the heat sink. The 10-watt power over fiber has a heat sink with a length of 10 centimeters and a cross-section area of 4 square centimeters. So it's a very long, heavy heat sink for that 10-watt unit. But compared to the transformer-based solution, still that actually possibly has higher power density. And again, you have a 100% elimination of common mode noise coupling.
Okay, thank you. The second question is, are the voltage ratings for the power supply shown on slide 12 high pot test values or continuous operation values?
Slide
high potential.
So I think you are talking about the isolation voltage. If that's the case, then basically this continuous operation isolation voltage. This means actually in nowadays power supply designs with very low power. This we are talking about 6 watt and very low input voltage, 24 watt, very low output voltage, 5 watt. With this kind of power supplies, if we build the isolation inside, it's not big at 10 kV, and also it's not difficult to realize it because again it's low voltage input, low voltage output. So you have this kind of good performance with existing solutions. That is the reason when you look at the gate drive board at the bottom, we do not have big devices. The power modules actually started on the other side. So basically, it's a very small unit. I do have another board actually to do the SPI connection, and the 6-watt power supply is on the other board, which will be the interface board to this. And that one actually is half size of this board.
Okay, thank you. I don't see any other questions coming through the chat window, so if anyone has any other questions, we certainly have time. Just unmute yourself and speak your question.
Any questions will be welcome.
Okay, I don't see any questions coming through. Last chance, any additional questions for Dr. Wang? Okay, I guess not. You were just such a good speaker. You provided all the information needed.
Well, if anybody has some questions in your mind now or later, please feel free to email me. Or actually, I guess I will see a lot of you in WIPDA in the next week. We can also chat over there.
Excellent. Well, thanks very much, Dr. Wang. I'm glad that this project is progressing well and that you're potentially getting a patent out of it and using some pretty innovative technologies such as the power over fiber based isolation, although it's pretty high cost right now. So thank you very much for your time, and thank you to all the participants.
Thanks for inviting me for the presentation. I really appreciate it.
Okay, thanks everyone for joining us today. Please join us again on November 7th when we'll have our next